Usually when we talked about a medical diagnosis, there's this expectation of precision.
Right, like it's engineering or something.
Exactly. I mean, you break your arm, the X-ray shows that jagged white line, and the doctor just points and says, there it is.
Yeah, it's very binary, broken or not broken. We inherently like things to be visible, to be categorized neatly based on their physical location in the body.
Because it gives us a sense of control over the disease.
Totally.
But then you step into the world of blood cancers, and suddenly that X-ray machine is, well, it's basically useless. We're looking at a diagnostic landscape that is completely counterintuitive.
Oh, absolutely.
So welcome to today's deep dive. We've got a fascinating stack of medical history, biological mechanisms, and modern treatments to go through today. Because to actually understand the pathophysiology of leukemia and lymphoma, how these blood-forming cells go rogue for you, the listener, we first have to unlearn almost everything we think we know about their names.
Yeah, the textbook definition, the one most of us have in our heads, it draws a very strict boundary.
Right.
It dictates that leukemia is a malignancy in the blood and the bone marrow, while lymphoma is, a malignancy in the lymph nodes and lymphoid tissues, like the spleen or the thymus.
So leukemia is in the blood, lymphoma is in the nodes.
That's the classical way to think about it. But our sources today completely shatter that strict anatomical boundary. It's an illusion.
Okay, let's unpack this. Because how can a physical location just be an illusion?
Well, that distinction was never really based on a clean biological boundary. It was simply a description of where doctors happened to look historically.
Because they didn't have the tools we have now.
Right, before modern molecular diagnostics existed. To give you a perfect clinical example from the sources, let's look at chronic lymphocytic leukemia, or CLL, and small lymphocytic lymphoma, SLL.
Two different names, which implies two completely different diseases in two different locations, right?
You'd think so, yet they are the exact same malignant clone of D cells. The World Health Organization, especially in their recent revisions, classifies them as one single disease entity.
Wait, really? One disease?
One disease. The only difference is the pattern of spread at the exact moment the doctor makes the diagnosis. If the abnormal cells are mainly circulating in the bloodstream, they label it CLL.
Yeah.
If those identical cells happen to be packed into the lymph nodes, they label it SLL. A patient can present with SLL, and then years later, that identical clone of cells spills over into the blood.
And suddenly it's CLL.
Exactly. Suddenly it's labeled CLL, even though the biology of the tumor never changed at all, just its anatomical distribution.
Wow, so it's like a traffic jam. Whether the cars are jammed up on a highway, which would be the leukemia, or packed tightly into a parking lot, which is lymphoma, it's the exact same type of car causing the problem.
That is a great way to picture it.
But I have to push back on the medical community here a bit. Why did it take us so long to realize this if it's the exact same cell?
What's fascinating here is that historically, pathologists only had microscopes. They had to classify diseases by morphology.
Meaning what the cell physically looked like?
Right, what it looked like in anatomy, so where they found it. But modern medicine is decisively moving away from that. We are shifting toward genetic and molecular definitions.
So the location is secondary now.
Today, the driving factor isn't what the cell looks like. It's what mutations and translocations drive it. So a disease's name is increasingly becoming more of a genetic sentence.
A genetic sentence.
Yeah. Instead of just saying a cancer of the lymph nodes, a diagnosis sounds more like B lymphoblastic leukemia lymphoma with BCR-ABL1 fusion.
Which is a mouthful.
It is, but it's precise.
And that completely changes how we approach the disease. If it's a genetic issue rather than a location issue, we need to lean in on the biological factory where these cells are made, right? To see exactly where the assembly line breaks down.
Absolutely. To understand the malfunction, you first have to visualize the normal factory.
Okay, set the scene for us.
Deep inside your bone marrow, all blood cells, red cells, platelets, white cells, descend from a tiny, self-renewing population of hematopoietic stem cells.
So think of these stem cells as the raw, undifferentiated material.
Exactly. They divide and branch down highly regulated pathways. There is the myeloid branch, which ultimately becomes your oxygen-carrying red cells, your clotting platelets, and certain infection-fighting white cells.
And the other branch?
That's the lymphoid branch, which becomes your targeted immune system, so your B cells and T cells.
And at each step on that assembly line, there are transcription factors, right? Like proteins that act like foremen, turning specific genes on and off, telling the cell to mature to the next stage.
Right, they guide the cell's maturation. But malignancy happens when a cell on this pathway acquires a specific two-part mutation.
Two parts. Okay, what's the first part?
First, there is a differentiation block. The cell loses the ability to respond to those transcription factors. It basically freezes at an immature stage.
You get stuck.
Yeah, often called a blast. It can't grow up into a functional cell. And then second, there is a proliferative advantage. It gains the ability to divide endlessly without dying on schedule.
So it's like a mechanical failure on a factory conveyor belt. The machinery that stamps the final parts breaks down. That's the differentiation block, so nothing gets finished.
Precisely.
But the raw materials keep pouring in at lightning speed. That's the proliferative advantage. So the factory floor just floods with millions of identical, useless, half-finished parts.
That captures the physics of it perfectly. And because this assembly line has so many different stages where the belt can break, we have a whole cluster of neighboring terms that can sound confusing.
Like myeloma, right? We hear that a lot.
Yeah, myeloma arises when the break happens at the very end of the line in terminally differentiated plasma cells, the mature B cells that produce antibodies.
And then there's MDS.
Myelodysplastic syndrome, right, which is a pre-leukemic disorder. The factory is producing abnormal cells that die off too quickly, leading to low blood counts. But MDS can easily acquire more mutations and transform into full-blown acute myeloid leukemia, or AML.
Wait, if our stem cells are dividing every single day of our lives, mutations must be happening constantly. Why doesn't every 80-year-old develop leukemia? Is there a middle ground state where the mutation happens but the cancer doesn't?
There is, actually, and it's a critical area of modern research called clonal hematopoiesis. It's heavily seen in older adults.
What does that look like?
A stem cell acquires a leukemia-associated mutation and quietly clones itself. But it doesn't cause a differentiation block, it doesn't cause disease, it just modestly raises the patient's lifetime risk of developing one.
So it's just hanging out.
Pretty much. It shows that our bodies tolerate a surprising amount of genetic error before the system actually crashes.
Since we are talking about these immature cells multiplying relentlessly in the marrow and spilling into the blood, I have to ask about how this spreads. When we think of cancer, we normally think of a solid lump that breaks off and travels to other organs. Does the concept of metastasis even apply here?
It does not. Applying solid tumor logic to blood cancer is a massive misconception.
Really? No metastasis at all?
No, because blood cancers don't metastasize in that way. Leukemic cells are, by their very nature, already circulating. The entire premise of the disease is that it is a systemic population of abnormal cells from day one.
Because they live in the blood.
Exactly. They don't need to break through a basement membrane and invade a blood vessel. They are born in the blood vessels. That's why solid tumor concepts, like surgical removal, are largely irrelevant to leukemia. You can't just cut it out.
That makes total sense. And if you're listening to this, you've probably had routine blood work done, like a CBC, a complete blood count. That systemic nature is exactly why blood cancers can often be flagged on a routine lab draw.
Right. It's everywhere in the blood.
But how were doctors supposed to figure out this complex systemic factory malfunction 150 years ago? I mean, they couldn't just sequence DNA back then.
No, they definitely couldn't. They had to rely on the absolute cutting-edge technology of the 1840s, which was slightly better lenses in their microscopes.
Which feels so primitive now.
It does. But in 1845, the word leukemia was actually coined independently by two different people working continents apart within months of each other.
In Germany, you have Rudolf Virchow, who is widely considered the father of modern pathology. The sources mentioned he looks at a patient's blood under a microscope and sees it packed with white cells instead of red.
Right.
So he calls it Weiss's Blut, meaning white blood, which he later Latinized to leukemia.
And at almost the exact same time in Scotland, John Hughes Bennett sees a similar case. But Bennett incorrectly guesses that the dense white material is pus.
Oh, wow.
Yeah, he calls it suppuration of the blood, assuming it's a massive blood infection. Virchow correctly realized it was a primary disease of the blood cells themselves, rather than a response to an outside infection.
Which is why Virchow gets all the historical credit today.
Exactly.
And lymphoma has an even older and arguably more frustrating origin story.
Definitely. In 1832, Thomas Hodgkin in London described patients with dramatically enlarged lymph nodes and spleens, but he didn't have a microscope capable of seeing the cellular pathology.
He was just looking at the gross anatomy.
Right. It wasn't until around 1898 and 1902 that Carl Sternberg and Dorothy Reed independently identified the malignant cell that actually defines classic Hodgkin lymphoma.
It's this massive bilobe cell that looks like an owl's eye under the microscope, right?
That's the one.
And the sources point out something incredible about Dorothy Reed. She was one of the first women admitted to Johns Hopkins medical program. Her paper in 1902 was vastly more rigorous than Sternberg's in ruling out tuberculosis as the cause.
It was a brilliant piece of work.
Yet convention still often lists his name first, calling it the Reed-Sternberg cell, or even prioritizes Sternberg in the older literature.
It's a sad historical bias, but identifying that specific owl's eye cell gave us Hodgkin lymphoma. The problem is, it inadvertently created a massive taxonomic problem for the next century.
How so?
Well, all other lymphomas that didn't happen to have that specific cell were just lumped into a catch-all category called non-Hodgkin lymphoma.
Wait, so every other lymphoma is just named after what it isn't?
Basically, yeah.
Isn't that an incredibly unhelpful way to classify dozens of fundamentally different diseases? I mean, it's like classifying all vehicles on the road as either Ford Mustangs or non-Ford Mustangs.
It is incredibly unhelpful, and this raises an important question about how we define illness itself. For decades, pathologists resisted shifting away from visual classification systems like the old Rappaport system because looking at the physical shape of cells under a microscope was what routine hospital labs were set up to do.
Even if it meant grouping together diseases with wildly different underlying biologies just because the cells looked similar in size.
Precisely. It wasn't until the 1990s and early 2000s that the medical field fully embraced defining these diseases by their immunophenotypes.
Immunophenotypes, meaning the specific protein flags on the surface of the cells.
Right, that and their genetics. Pathologists resisted at first because molecular testing was complex and it was expensive, but genetic classification ultimately won out because it is infinitely better at predicting how a patient will actually respond to therapy.
And that shift toward genetic classification didn't just happen because of better lab equipment. It was driven by a landmark discovery that proved, for the very first time, that cancer could be traced to a single targetable genetic typo.
The Philadelphia chromosome.
Yes.
In 1960, Peter Knoll and David Hungerford noticed that patients with chronic myeloid leukemia, or CML, consistently had one abnormally short chromosome in their leukemic cells.
Which was huge.
Massive. This was the first consistent genetic abnormality ever linked to a human cancer.
But noticing a short chromosome is one thing, figuring out why it causes cancer is another. It took another 13 years until 1973 for Janet Rowley at the University of Chicago to decipher it.
Yeah, using new chromosome banding techniques, she proved it wasn't just a deletion where DNA went missing, it was a translocation.
Explain a translocation for us.
It's a reciprocal swap of genetic material between chromosomes. In this case, chromosomes 9 and 22 physically break and trade pieces. It fuses two genes together, BCR and ABL1, creating a brand new mutant fusion protein called BCR-ABL.
Here's where it gets really interesting. Because the sources note this fusion protein acts as a permanently stuck-on pyrosine kinase switch. But what does a kinase actually do? Like, why does a suck switch cause leukemia?
Think of a kinase as a molecular courier delivering a green light signal. It's an enzyme that attaches a phosphate group to other proteins, which acts as a chemical signal telling the cell to divide and survive.
Okay, so it's the green light for cell division.
Normally, yes. A kinase only fires when it receives an external signal, like a growth factor. But the BCR-ABL fusion protein is deformed. Its structure is stuck in the active firing position.
It never turns off.
Never. It relentlessly bombards the cell with signals to divide, completely independent of the body's actual needs.
And once you know exactly which switch is stuck in the on position, you can build a physical tool to turn it off.
Exactly.
In 2001, Brian Drucker's team developed a drug called imatinib, or Gleevec. It physically binds into the pocket of that BCR-ABL protein, blocking the ATP energy molecule it uses to function. It literally turns the switch off.
It's a masterpiece of drug design.
It's like finding the one single cut wire in a massive, sprawling electrical grid and just taping it back together, rather than blowing up the whole building with traditional chemotherapy.
The clinical results were unprecedented. I mean, imatinib converted CML from a disease with a median survival of just 3 to 5 years into a chronic condition where most patients now have a near-normal life expectancy just by taking a daily pill.
That is just incredible.
It proved that if you understand the molecular mechanism, you can stop the cancer without destroying the healthy cells. It is the absolute gold standard for targeted precision oncology.
Well, imatinib is this elegant precision sniper shot. Historically, doctors had to rely on sheer brute force to stop these rapidly cloning cells. And that brute force era led to both incredible triumphs and some truly mind-bending discoveries about what triggers these mutations in the first place.
Oh, the brute force approach was born out of pure desperation, particularly with childhood acute lymphoblastic leukemia, or ALL. In the 1950s, childhood ALL was essentially a death sentence. Survival was measured in months.
It's heartbreaking to even think about.
It was grim. At the National Cancer Institute, researchers Tom Freireich and Emil Frey pioneered a radical idea: combination chemotherapy.
The VAMP regimen, hitting the body with 4 different toxic drugs simultaneously. But why combination? Why not just use one strong drug?
Because of clonal evolution. If you use one drug, you might kill 99% of the cancer cells, but the 1% that happens to have a random genetic resistance will survive and repopulate the marrow.
So they just mutate around it.
Right, but by hitting them with multiple drugs that operate on entirely different mechanical pathways, say one that shreds DNA and another that destroys the cell's structural scaffolding, you mathematically eliminate the cancer's ability to mutate its way out.
But the side effects were horrific, weren't they? The sources mentioned Freireich was widely accused of cruelty for pushing such toxic treatments on dying children.
The toxicity was immense. It caused fatal hemorrhages, which forced Freireich to also pioneer the modern platelet transfusion just to keep the patients from bleeding to death during the treatment.
Just to survive the cure.
Exactly. But that sheer brute force worked. Today, the cure rate for childhood ALL is roughly 90%. It is one of the greatest success stories in medical history.
And around that same time, another wild discovery was unfolding. In 1958, a British surgeon named Dennis Burkitt was working in Uganda. He mapped out a fast-growing childhood jaw tumor across equatorial Africa, and he noticed the geographic pattern perfectly matched endemic malaria zones.
Which is such a brilliant observation.
He suspected an infectious agent was at play.
Right. And in 1964, virologists Michael Epstein and Yvonne Barr examined the tumor samples Burkitt sent them. They discovered a previously unknown herpes virus, which we now call the Epstein-Barr virus, or EBV.
The first virus definitively linked to a human cancer.
Yes.
Wait, how does a virus cause a blood cancer? Does it just walk in and rewrite our DNA? Does that mean you can, catch lymphoma from someone coughing on you?
If we connect this to the bigger picture, it's vital to separate the virus from the cancer. You cannot catch lymphoma.
Okay, good to know.
The virus, EBV, is highly contagious. In fact, most adults on Earth have been exposed to it. But EBV doesn't directly cause the cancer by mutating the DNA itself. It inserts its own episomal DNA into the B cell, which drives relentless cellular proliferation and inflammation.
So it stresses the system out.
The virus effectively forces the cell to multiply rapidly. And when cells are multiplying that fast, the biological machinery makes mistakes. It sets the stage for a critical translocation involving the MYC oncogene.
Ah, I see.
So the cancer is a secondary genetic accident caused by the viral stress, not a transmissible disease itself.
Okay, so we've gone from brute force chemo to finding viral triggers, and now modern medicine is in the era of designer cells.
Oh.
We're turning the patient's own immune system into the targeted therapy.
CRT cell therapy. It's revolutionary. In 2012, a 6-year-old patient named Emily Whitehead with relapsed ALL was treated by Carl June's team using her own genetically engineered T cells.
But how do you reprogram a human cell? You can't just type new code into a computer.
You have to hijack a biological courier. They extract the patient's T cells and then use a deactivated virus, often a modified lentivirus related to HIV, to insert a new gene into the T cell's DNA.
A virus to fight the cancer.
Yes, a viral vector. This new gene instructs the T cell to build a synthetic protein called a chimeric antigen receptor, or TARR. This synthetic receptor is perfectly shaped to recognize and bind to a specific protein, usually CD19, which is found on the surface of the leukemia cells.
And then what?
They multiply these assassin cells by the millions in a lab and infuse them back into the patient.
It's science fiction level medicine. You are deploying a synthetic army. But it brings us to a stark clinical reality. The first approved CAR-T product, Kymriah, launched with a list price of around $475,000 for a single infusion.
The development of CAR-T is a medical marvel, but its price tag is an objective reality of modern oncology that doctors and hospital systems are wrestling with today. The highly individualized manufacturing process culturing a bespoke living drug for every single patient creates unprecedented costs.
Which factors heavily into discussions about health equity and access to life-saving therapies, obviously.
Huge equity debates.
It's a massive logistical challenge. And speaking of challenges, sometimes the hardest part of modern medicine is doing something completely counterintuitive. We now have combination chemo, targeted kinase inhibitors, and multi-million-dollar engineered cells. But paradoxically, sometimes the best thing to do with all this advanced knowledge is, well, absolutely nothing.
The watch and wait strategy. For indolent or slow-growing lymphomas like early-stage CLL or follicular lymphoma, multiple randomized trials over decades have proven that starting chemotherapy immediately at diagnosis does not improve overall survival.
If you're a patient, imagine being told you have leukemia and the oncologist says, cool, let's just monitor your blood work every 6 months. That goes against every human survival instinct. You want to eradicate it immediately.
Oh, it causes immense psychological anxiety, but biologically, the data is irrefutable. Early treatment exposes the patient to the toxicities and secondary cancer risks of chemotherapy without extending their life by a single day. You only treat if the disease begins to cause organ dysfunction or severe symptoms.
That's wild.
It ties directly into a major public misconception about the clinical labels acute and chronic. People assume chronic means a mild, manageable condition, and acute means an automatic death sentence.
But in hematology, those terms don't mean what the public thinks they mean, do they?
Not at all. Acute and chronic describe the tempo of the disease at the moment of diagnosis and the maturity of the cells involved, not the ultimate severity.
Okay, so chronic leukemias.
Chronic leukemias involve mature-looking cells that multiply slowly. They can smolder for years, but they can spontaneously acquire new mutations and transform into a highly aggressive, rapidly fatal blast crisis.
And acute.
Conversely, acute leukemias, like pediatric AL, involve immature blast cells that multiply furiously. They require emergency, immediate treatment, but because they are dividing so fast, they are often highly susceptible to chemotherapy and are largely curable today.
We really have to respect the biological mechanics over our instincts. And when the medical community ignores those mechanics, things go terribly wrong. The sources provide a chilling cautionary tale about this from the 1980s and 90s regarding high-dose chemotherapy and autologous bone marrow transplants.
Yeah, to understand the failure, you have to understand the mechanics of the transplant. In an autologous stem cell transplant, doctors harvest the patient's own healthy stem cells and freeze them. Then, they hit the patient with megadoses of chemotherapy doses so high they completely destroy the bone marrow.
It's essentially lethal.
It is lethal.
Yeah.
But then they rescue the patient by infusing the thawed stem cells back into the blood, where they home back to the marrow and rebuild the immune system.
It's a brilliant rescue mission, and it works for blood cancers. But in the 90s, there was an intense push to use this for solid tumors, specifically breast cancer.
And the logic was just flawed. Upping the dose of chemo doesn't proportionally increase the kill rate for solid tumors the way it does for circulating liquid tumors.
They did it anyway.
The push to do it was heavily driven by fraudulent clinical trial data published by a South African researcher named Werner Bezwoda. He completely flummocated data showing massive survival benefits.
That is horrifying.
It is. It is taught today as a prime example of how a legitimate, powerful therapy for blood cancer can be dangerously oversold into contexts where the biological evidence simply does not support the mechanism.
It's a sobering reminder that as fast as molecular science moves, rigorous mechanistic evidence has to be the anchor. So let's bring it all together for you. We've covered an incredible amount of ground today. We learned that leukemia and lymphoma are essentially patterns of spread. The highway versus the parking lot? Not fundamentally different diseases. We've seen how diagnoses transformed from visual descriptions of owl's eyes under a microscope to genetic sentences of translocations and kinases. We've traced the mechanics from brutal combination chemotherapy to how viruses like EBV stress the genome, all the way to using viral vectors to engineer our own synthetic T cells.
This deep dive into blood cancer matters profoundly because this field is the vanguard of modern medicine. Blood cancer research built the foundation of precision oncology. It's a massive driver of pediatric medicine.
And it connects to other diseases too, right?
Absolutely. It's even unlocking mysteries in entirely different physiological systems. For example, the Epstein-Barr virus, which was discovered because a surgeon mapped Burkitt lymphoma, was just recently linked as a likely underlying trigger for multiple sclerosis.
Oh, wow. MS.
Yeah. Research into malignant blood cells is actively mapping the human immune system and the origins of autoimmune neurology.
It's all connected. Which brings us to one final thought for you to mull over. We talked about Dennis Burkitt, who just happened to notice a geographic pattern on a map matching malaria zones, which led to the discovery of the very first virus ever linked to human cancer. With all the big data we generate today, From our smartwatches, our electronic health records, our genetic sequencing, what other environmental triggers are hiding in plain sight, just waiting for us to connect the dots in the data. Thank you for joining us on this deep dive. Keep questioning the world around you, and we'll see you next time.